Hey everyone, welcome to a video on solving inverse trigonometric functions. In order to understand how to solve inverse trig functions, it's really important to understand how to solve regular trig functions first. Just as a really quick review here, if you had a 30, 60, 90 triangle and you had to find sine of 30 degrees, that's just going to be the opposite over hypotenuse, or the y over the r, and that's just going to be 1/2. When we have a regular trig function like sine, cosine, or tangent, we're taking that of an angle here. And the result is a ratio. As a strategy to remember this, it's very possible that you've learned SOHCAHTOA in the past so that you could solve regular trig functions. Let's consider this the old stuff. If you'd like me to make a video on solving regular trig functions, comment down below and I'll do so. That brings us to the new stuff. Notice these little -1s next to the regular trig functions. Whenever we see a trig function with a little -1, it means that we're finding an inverse trig function. We're not going to be looking for a ratio, but rather we're going to be looking for an angle. This could be measured in degrees or radians. Notice how the regular trig functions are of angles, while the inverse trig functions are of ratios. And notice what kind of answers we get. While regular trig functions get us a ratio, inverse trig functions get us an angle. Simply put, if we knew that sine of 30 degrees was equal to 1/2, then inverse sine, or arc sine, of 1/2 is equal to 30 degrees. Please note that when using inverse trig functions, the ratio and the angle measure switch places. Let's dive a little bit deeper into these. At this point, I hope you're familiar with the unit circle. The content on the screen here is meant to show you that the unit circle is really made up of these 30, 60, 90, and 45, 45, 90 triangles. It's really important to understand that these special right triangles are really scaled down for the unit circle. By dividing each of the measurements on the 30, 60, 90 triangle by 2 here, you see we get a similar right triangle here with the same exact angle measures, just scaled down measurements. Dividing each of the side lengths of a 45, 45, 90 triangle by the square root of 2, we're actually going to get these scaled down measurements of 1, root 2 over 2, and root 2 over 2. Although this is also another 30, 60, 90 triangle, it's turned sideways here, so I'm just going to show that by dividing all these by 2, we do get this 1, this 1/2, and this root 3 over 2. So why did we scale down these right triangles? The importance of doing this is to see that all of the hypotenuse here are 1. This hypotenuse here of 1 corresponds to the radius of the unit circle, which is right over here. This 1 over here, which is the hypotenuse for the 45, 45, 90, represents the radius of the circle again. And finally, this 1 over here represents the hypotenuse one more time, which is also the radius of the circle. While it's easy to see the radius of the circle vertically here and horizontally, sometimes it's lost in translation that the hypotenuse of these right triangles also represents the radius. By that logic, each of these ordered pairs on the unit circle represent an x and a y, and it makes sense here that the x value is horizontal distance, which is right over here, which represents this 1/2, and the vertical distance here, which represents root 3 over 2. This ordered pair does the same thing here, where the horizontal distance is x, which is right over here, and the vertical distance is y, which is right over here. And one more time, this x and y value here correspond with the horizontal and vertical distance of the 30, 60, 90 triangle. Hopefully this gives you a little bit better background story on how the special right triangles relate to the unit circle. Now if you're at the point that you don't really care about the unit circle and you just want to know what the values of trig functions are, this table represents all the ratios you'll get when using the 6 trig functions on 30, 45, 60, and 90 degrees. Rather than drawing or memorizing the unit circle, you can always make this table by using the 30, 60, 90, and 45, 45, 90 triangle ratios. Over here on the right, it's important that we take note of the range of these inverse trig functions. For all of our inverse sine functions, our answers have to be between -90 degrees and +90 degrees. For all of our inverse cosine functions, the answers have to be between 0 degrees and 180 degrees. And like the inverse sine function, the inverse tangent function has the same range of -90 degrees to +90 degrees. Knowing these ranges will help you narrow down where your answer has to be. Here you can see I drew some visuals to help you understand where the answers can be for each of these inverse trig functions. When solving inverse sine functions, your solutions have to be in either quadrant 1 here or quadrant 4. If you got an answer outside of these two quadrants, you made a mistake. Make sure you don't write an answer for an inverse sine function outside of these two quadrants. For inverse cosine functions, the answers have to be in either quadrant 1 or quadrant 2. And similar to the arc sine function, the answers for the arc tangent functions have to be in quadrant 1 or quadrant 4. While I know this is a lot, I need you just to take a deep breath and work with me here. This video is all about solving these types of problems and understanding how these inverse functions are related to their normal functions. Let's dive into some examples now. Grab something to write with and some paper and try some examples with me. Pause often, take screenshots, replay parts, and use the timestamps to help you understand these much better. Let's try some examples now. In example 1, let's try solving some inverse sine functions. Here we're trying to find the inverse sine, or arcsine, of the square root of 2 over 2. Since it's an inverse trig function, remember that we're looking for an angle. I'm going to use theta here to represent what we're looking for. The angle we're looking for must lie between 90 degrees and negative 90 degrees, or between pi over 2 and negative pi over 2. Since we have a root 2 here, we know we're talking about the 45-45-90 triangle because that has a root 2 in it. Looking at this 45 degrees right here and remembering our SOHCAHTOA, we can say the sine of 45 degrees is going to be opposite over hypotenuse. Here's our opposite, and here's the hypotenuse. From that, we can say that sine of 45 degrees is going to be 1 over the square root of 2. To rationalize this, we're going to multiply it by the square root of 2 over the square root of 2, and that's going to equal the square root of 2 over 2. Let's look at each of the 45-degree reference angles here. Right here is 45 degrees, and we know that's going to be root 2 over 2. Over here in quadrant 2, this is going to be 135 degrees. Sine of 135 degrees is going to be square root of 2 over 2. This 45-degree reference angle down here is going to be 225 degrees. Sine of 225 degrees is going to be negative square root of 2 over 2. And finally, if we take sine of this reference angle down here, which is going to be 315 degrees, we can say sine of 315 degrees is equal to negative root 2 over 2. Since we're looking for a positive root 2 over 2, these second two choices are no good. 315 degrees is not the answer, and 225 is also not the answer. That narrows our answer choice down to either 45 degrees or 135 degrees. From using the reference angles, you can see that they both algebraically get root 2 over 2. However, remember a range restriction for inverse sine tells us that we can only have angle measures that are between negative 90 degrees and positive 90 degrees. Since 135 degrees doesn't fit in the range, this can't be it. In conclusion, we can say that theta, or the angle measure, is equal to 45 degrees, or we can convert this to radians and say that's pi over 4. This would be our answer for the first one. We've now concluded that the inverse sine of the square root of 2 over 2 is equal to 45 degrees. If you want to verify this, you can ask yourself, what's sine of 45 degrees? If you do that, you should get the square root of 2 over 2. That's how we know that we are correct. Let's try another one together. Here we're going to find arcsine of negative root 3 over 2. We're going to be looking for an angle measure again. Since we have a square root of 3 in our ratio here, we should look at one of the 30, 60, 90 triangles. They're both the same triangle, just turned sideways, depending if we need 30 degrees or 60 degrees. I'm going to choose this one, and you'll see why in just a moment. Let's use this as our angle measure and say sine of 60 degrees. If we take sine of 60 degrees, again, that's going to be opposite over hypotenuse. Here's our opposite side, and here's our hypotenuse. The sine of 60 degrees should be equal to the square root of 3 over 2. Well, it's close to being what we want. We actually want a negative square root of 3 over 2 instead of a positive root 3 over 2. Let's look at all the reference angles for 60 degrees. We just found out what sine of 60 degrees is, and that's going to be in quadrant 1. What about in quadrant 2? In quadrant 2, we can also draw a 60-degree reference angle. This over here is the same thing as 120 degrees. Sine of 120 degrees is going to equal root 3 over 2. Remember, sine is positive in quadrant 2. And here's our reference angle for 60 degrees in quadrant 3. This is 240 degrees. Sine of 240 degrees is going to be equal to negative root 3 over 2. Remember, sine is always negative in quadrant 3. And here's our last 60-degree reference angle in quadrant 4. Sine of 300 degrees is equal to negative root 3 over 2. Since we're looking for a negative root 3 over 2, 60 degrees can't be it, 120 degrees can't be it, and since 240 degrees is over here in quadrant 3, it falls outside of the range of our function, so 240 degrees can't be it, so we must go with our 300 degrees here. Since 300 degrees doesn't fit between negative 90 and positive 90 degrees, we can also think of this as negative 60 degrees. Negative 60 degrees is in the same location as 300 degrees, and it fits in the range. Here we find that our theta, or our angle measure, is going to be negative 60 degrees, or we can write this in radians saying it's negative pi over 3. This is our answer. We just found that the inverse sine of negative root 3 over 2 is equal to negative 60 degrees. You can check this by taking the sine of negative 60 degrees and seeing if it is actually equal to negative root 3 over 2. Now let's find arc sine of negative 1. Let's see what angle measure this is equal to. To get started here, remember that sine of an angle measure is equal to y over r, cosine of an angle is equal to x over r, and tangent of an angle is equal to y over x. Since we're dealing with sine here, we just need this first one. This r here really represents the radius of a unit circle, and that's always going to be equal to 1. And this y here is referring to a y coordinate. Since we know the denominator is 1, the numerator must be negative 1. Looking at a unit circle, there's only one location on here where y is equal to negative 1. Y is equal to 0 here, y is equal to positive 1 here, y is equal to 0 again over here, and y is equal to negative 1 over here. This one right here is the one that we want. Yay. So here we get sine of theta is equal to negative 1 over 1, which is negative 1. Now what angle measure gets us that? We can see here that that angle measure is 270 degrees. We found here that sine of 270 degrees is equal to negative 1. Since that's true, we can say that the inverse sine of negative 1 is equal to 270 degrees. Looking at our range here, we can clearly see that 270 degrees doesn't fit between negative 90 and positive 90. So instead, let's rewrite this 270 degrees as negative 90 degrees. In this problem, theta is equal to negative 90 degrees, or in radians, it's going to be negative pi over 2. This is our answer here. Let's try one more that looks a little bit different. This is a composite inverse trig function. Since this is an inverse or arc sine here, we're still going to be looking for an angle measure. Since this one's a little bit different, I'm just going to rewrite the problem. We have inverse sine or arc sine of the sine of 7 pi over 6. This is equal to some angle measure. As usual, let's start with our inside function and work our way out. Let's figure out where 7 pi over 6 is. Here we're going to start at 0 degrees, and we know pi is the same thing as 180 degrees, so 7 pi over 6 has to be a little bit more than 180. Let's put it right over here. Since 7 pi over 6 is the same thing as 210 degrees, we know that this is a 30-degree reference angle here. I'm just going to draw a vertical line down to complete a right triangle to use. Since this is a 30, 60, 90 triangle, we can write our ratios here of 1 to 2 to root 3. Looking at sine of 7 pi over 6, we can really just find sine of 30 degrees. Here's our opposite, and here's our hypotenuse. Since the sine of 30 is going to be opposite over hypotenuse, or 1 over 2, we can then say that sine of 7 pi over 6 is going to equal negative 1/2. The reason why it's negative is because we're in quadrant 3. Sine is always negative in quadrant 3. Now that we know that sine of 7 pi over 6 is negative 1/2, let's substitute that back in. Here we can rewrite the inverse sine of negative 1/2, we just found that out, is equal to some angle measure. Since we have a 1 and a 2 in our ratio, I'm going to use this 30, 60, 90 triangle because it has a 1 and a 2 in it. Sine of 30 degrees is going to be equal to 1/2. That's positive here because all the trig functions are positive here in quadrant 1. If we draw a 30-degree reference angle here in quadrant 2, this is 150 degrees. Sine of 150 degrees is also equal to 1/2. Remember, sine's positive in quadrant 2. Drawing our reference angle here in quadrant 3, this angle measure is going to be 210 degrees. Sine of 210 degrees is equal to negative 1/2. And here's our last reference angle. This angle measure here is going to be 330 degrees. Sine of 330 degrees is going to be negative 1/2. Remember, only cosine is positive in quadrant 4. Since we're looking for negative 1/2 here, 30 degrees won't work, and 150 degrees won't work. Those resulted in positive 1/2. Let's just focus on 210 degrees and 330 degrees because they both get us negative 1/2. The problem with 210 degrees is that it lies in quadrant 3. Remember, the range for inverse sine functions is restricted to quadrant 1 and quadrant 4. Based on that, 210 degrees can't be the answer. 330 degrees must represent our answer. Since it's not between negative 90 and positive 90 degrees, let's rewrite it as negative 30 degrees, since they're the same thing. In conclusion here, we're going to say that the angle measure here is negative 30 degrees, or in radians, we can say that this is going to be negative pi over 6. This is our final answer. In example 2, let's try solving some inverse cosine functions together. Let's find out what inverse cosine of negative 1/2 is equal to. I'm going to start by looking at a 30, 60, 90 triangle and looking at this 60 degrees. The reason why I'm choosing 60 degrees is because if you do cosine of 60 degrees, that's going to be adjacent over hypotenuse. Looking at the values here, we have 1 over 2. Cosine of 60 degrees is going to be equal to 1/2. While it's close to what we want, it's not the right sign. Let's see what other options we have here. Here, I'm drawing 60 degrees. We know cosine of 60 degrees is 1/2, and that's not correct. Drawing the reference angle for 60 degrees in quadrant 2, that's going to be 120 degrees. Cosine of 120 degrees is going to be negative 1/2, and that's because cosine is always negative in quadrant 2. Heading over to quadrant 3 here, this angle measure is going to be 240 degrees. Cosine of 240 degrees is going to be equal to negative 1/2, and that's because cosine is also negative in quadrant 3. And here's our last 60 degree reference angle in quadrant 4. This is 300 degrees. And if we take cosine of 300 degrees, that's going to equal positive 1/2. Since we're looking for a negative 1/2, we know 60 degrees can't be it, and 300 degrees can't be it. That narrows it down to 120 degrees and 240 degrees. Looking at the range values of our inverse cosine function, we can see that 120 degrees fits in the range, but 240 degrees doesn't. Let's get rid of this. Our angle here is going to be 120 degrees, or 2 pi over 3. That's our answer here. Now let's find out what angle inverse cosine of 0 is. Whenever you see a 0 or a 1 here, it's always a good idea to think about the unit circle. Remember unit circle ratios where sine of theta is equal to y over r, cosine of theta is equal to x over r, and tangent of theta is equal to y over x. In this example, we care about cosine of theta equaling x over r. R always represents the radius, and that's always going to equal 1 on the unit circle. And we need this x to somehow equal 0, because 0 divided by 1, or x over r, is going to equal 0. To find out where x is equal to 0, let's look at a unit circle here. At 0 degrees, we see that x is equal to 1. At 90 degrees, we see that x is equal to 0. At 180 degrees, we see x is equal to negative 1. And at 270 degrees, x is equal to 0. The two locations where x is equal to 0 is at 90 degrees and 270 degrees. So here we can write that cosine of 90 degrees is equal to 0, and we can write that cosine of 270 degrees is also equal to 0. Looking at our range restrictions over here to the right, we see that the angle we're looking for has to be between 0 and 180 degrees. That rules out 270 degrees. Which means our angle measure has to be 90 degrees. In this problem, the angle we're looking for is equal to 90 degrees, or we can say in radians that this is pi over 2. Now let's find what angle measure our cosine of root 3 over 2 is equal to. This root 3 and 2 remind me of the 30, 60, 90 triangle right away. Taking cosine of 30 degrees, that's going to be root 3, or the adjacent, over 2, which is the hypotenuse. Cosine of 30 degrees is going to equal root 3 over 2. Well, I'm not going to draw all the reference angles out for 30 degrees here. What I'm going to do is write their values. Cosine of 150 degrees is equal to negative root 3 over 2. And cosine of 210 degrees in the third quadrant is equal to negative root 3 over 2 again. And finally, in quadrant 4, if we do cosine of 330 degrees, that's going to equal positive root 3 over 2. Since we're looking for a positive root 3 over 2, this 150 can't work, and this 210 degrees also can't work. And since 330 degrees is in quadrant 4, which is not in our range, that can't work either. 30 degrees is the only angle measure that fits in our range of 0 degrees to 180 degrees and equals a positive root 3 over 2. The angle we're looking for here is equal to 30 degrees, or in radians we can say this is pi over 6. Here's our answer. Now let's solve a composite inverse cosine function. Here I'm just going to rewrite this. We have arc cosine, and we're going to do that to cosine of negative pi over 6. We're going to see what angle this is equal to. To begin, let's find out what cosine of negative pi over 6 is equal to. Here's where we're going to start. And pi over 6 is 30 degrees, so we have to go negative 30 degrees. So that's going to go over here into quadrant 4. Here we have 30 degrees, or the negative pi over 6. And if we draw a line straight up and down so that we get a 30, 60, 90 triangle here, this is going to be 1, this is going to be 2, and this is going to be root 3. Here we can see that cosine of negative pi over 6, or 30 degrees, is going to be equal to root 3 over 2. Let's copy that over here. So now that we know that cosine of negative pi over 6 is root 3 over 2, let's find the arc cosine of that value. See what angle measure that equals. Looking at this root 3 over 2 here, I'm going to look at this 30, 60, 90 triangle again. Cosine of 30 degrees is going to be adjacent over hypotenuse, or root 3 over 2. Here I'm just going to copy that down and write cosine of 30 degrees is equal to root 3 over 2. Writing out the other reference angles, cosine of 150 degrees, that's going to equal negative root 3 over 2. Cosine of 210 degrees is going to equal negative root 3 over 2, since cosine is going to be negative in quadrant 3. And our fourth one is going to be cosine of 330 degrees, and that's going to equal positive root 3 over 2, since cosine is positive in quadrant 4. Here's another way of thinking about eliminating some of these as options. We can see that each of these are located in different quadrants. We have one in quadrant 1, one in 2, one in quadrant 3, and one in quadrant 4. Since we know our answer or angle measure has to be in quadrants 1 and 2, we know we can cross out our angles that are in quadrants 3 and 4. And since we're looking for a positive root 3 over 2 and not a negative root 3 over 2, we can cross out this 150 degrees. Hopefully this makes more sense as to why our answer is going to be 30 degrees. Theta is equal to 30 degrees, or we can call this pi over 6. And that brings us to example 3. Let's try solving some inverse tangent functions. Let's start by finding the inverse tangent of negative 1. Let's just take a look at the tangent function. In order for this ratio here to be a value of 1, we need to have the same x and y value on top of each other. That rules out the 30, 60, 90 triangles, but it could be the 45, 45, 90 triangle because the x and the y have the same value. Taking the tangent of 45 degrees, that's going to equal 1 over 1, which is just going to equal 1. Taking the tangent of 135 degrees, that's going to be negative 1. Let's check out the range of our inverse tangent function here. It looks like our angle measure has to be in either quadrant 1 or quadrant 4. Since this one is in quadrant 2, we can cross this one out. Since 225 is in quadrant 3, that also can't be it. Since we're looking for a negative 1, not a positive 1, it can't be 45 degrees. That means it must be 315 degrees. Since the range says we must be between negative 90 and positive 90, let's rewrite this 315 degrees as negative 45 degrees. They're in the same location. The angle we were looking for is negative 45 degrees, or negative pi over 4. There's our answer. Now let's find arc tangent of root 3. Since it has a root 3 in it, it can't be a 45, 45, 90 triangle. Let's look at the 30, 60, 90 since it has a root 3 in it over here. Looking at our 45, 45, 90 triangle, we can see that tangent of 60 degrees is equal to root 3 over 1. That's just equal to root 3. Again, looking at our range, we have to have an angle measure that's in either quadrant 1 or quadrant 4. That rules out these two options that are in quadrants 2 and 3. And since we're looking for a positive root 3, it can't be 300 degrees. The angle we're looking for is 60 degrees. The angle we were looking for here is equal to 60 degrees, or in radians that's just going to be pi over 3. Now let's find arc tangent of negative root 3 over 3. Again, since we have root 3 again, we're not going to be looking at the 45, 45, 90 triangle. Instead, it makes more sense to look at this 30, 60, 90 triangle. Taking the tangent of 30 degrees, we can see here on our triangle that that is going to be 1 over the square root of 3. If we want to rationalize that denominator, we can multiply it by the root 3 over root 3, and that's going to equal root 3 over 3. Since that's not what we're looking for, let's find some of the other reference angles. In quadrant 2, the reference angle for 30 degrees is going to be at 150 degrees, and tangent 150 degrees is going to be negative root 3 over 3. That's better. In quadrant 3, our angle here is going to be 210 degrees. Tangent of 210 degrees is going to be positive root 3 over 3 again. And over in quadrant 4, if we do tangent of 330 degrees, we're going to find that that's equal to negative root 3 over 3. Looking at our range again over here, we can see that we only want an angle that's in quadrant 1 or quadrant 4, so we can get rid of this 150 degrees and this 210 degrees. And since we're looking for a negative root 3 over 3, we get rid of this 30 degrees up here. 330 degrees has to be our answer. Since that specific value doesn't fit between our range, we can rewrite this as negative 30 degrees. The angle we were looking for here is negative 30 degrees, or we can call this negative pi over 6. There it is. And here's the last example. Let's find the inverse tangent of 4 pi over 3. First, I'm just going to copy it down.
So we have the inverse tangent, and that's going to be of tangent of 4 pi over 3.
Just like in the last two composition functions, let's start with tangent of 4 pi over 3 on the inside. Starting at 0 degrees here, and if we look for 4 pi over 3, 4 pi over 3 is going to be greater than a full pi, so it's going to be over in quadrant 3. And I think that's going to be right around here. Drawing a line straight down here from the x-axis, we can see that we have a 60-degree angle here, which makes this 30 degrees, so this has to be a 1, root 3, and a 2, since this is a 30, 60, 90 triangle. Taking tangent of the 60 degrees here, that's going to be opposite over adjacent. So we find that tangent of this 4 pi over 3 is just going to be equal to root 3 over 1, or just root 3. Substituting in, let's find the arctangent of root 3. Looking at this 30, 60, 90 triangle here, we can see that tangent of 60 degrees is going to be opposite over adjacent, or root 3 over 1. So here I'm going to write tangent of 60 degrees is equal to root 3 over 1, or just root 3. One last time, our range restriction for these inverse tangent functions is going to be quadrant 1 and quadrant 4. So that rules out this 120 degrees and 240 degrees. And since we're looking for a positive root 3, this 300 degrees is out as well. That leaves us with 60 degrees. The angle we were looking for is equal to 60 degrees, or in radians we call that pi over 3. And that's the last one. Thanks for sticking through to the end of the video with me. I hope you found this useful in understanding how to solve inverse trig functions. If you found this video useful, feel free to like and subscribe, as well as comment with any future videos you'd like me to try and make. Keep up the good work, and I'll see you in the next one.